it's not particularly interesting. If this is cis or trans, it's going to do very similar chemistry. It's going to undergo very similar chemistry. So if generically speaking, this reacts with some atom AB, and AB has a dipole moment, so B, the generic atom B, is more electronegative than A, you would have this dipole going towards B, meaning that the A would have a partial negative, partial positive, the dipole's going away from that, and this would have a partial negative. So now I'll redraw this so it's not so cluttered. So here A, B, and then I won't show the dipole this time, just the partial charges. But the dipole explains why there's this difference in charges. So now when you look at these two things, we see that this is an electron-rich region. The double bond is similar in the sense of electron richness to a lone pair. There's a lot of electrons here that are available to create new bonds. So this is then going to function as a nucleophile, just like something that has a lone pair. The double bond is functioning in a similar way. So that means that this has to be our Lewis acid or our electrophile. So which one of these is going to be our electrophile, atom A or B? Well, it has to be A, because we know our electrophiles are electron loving, so they should have some positive charge or partial positive charge. So that's what we have here with this dipole. So A is going to function as our electrophile, and then B is just a part of that molecule. So how this general reaction would go is you use these two electrons from the double bond to create a new bond to A, and then you cleave the AB bond onto B to create a lone pair on B. So the reason you do this is, imagine if this is difficult because it's a generic atom, but bear with me, we'll do a specific. But let's say that A is a carbon and it already had 4 bonds. You couldn't create a 5th bond to it without simultaneously breaking one of the bonds to reduce it back to 4. So like, for instance, if you had this type of thing going on, then when the new bond is creating here, that would be the 5th bond. So this has to break at the same time. So that's why this general type of thing is going on. So the result of this is then going to be B minus is the easiest thing. So it's going to be B with our lone pair that we just created from the arrow for the bond breaking onto B, and that's a negative charge. And then this is the tricky thing. So we are adding a single bond to a carbon to A, but which carbon? And in this case, there's no preference, so you have to show both. So what I mean is, here's one option where A is binding to this first carbon. So we're using this double bond, so that double bond is gone, and then we're adding A to either carbon. So I'm adding it to this one first, the one on the left, which is here. Okay, so then now you have removed one bond from this carbon and we haven't created a new one. So that means that this has to be positively charged because it's lacking a 4th bond now, because the 4th bond was the double bond, and that double bond has gone now, and it's created this single bond to A, but it's done nothing to B here. So now you could, what I was referring to initially is you can now do it on the other side. You can add the A to the other side here, and you create the carbocation at carbon 1 that we have labeled from the previous example, previous definition. So is that, any questions on that? That can be hard to visualize, but if you see the double bond, you're creating a bond to either of those positions in a representation like this. So those two structures aren't resonant, it's just racemic product. So no, they're not resonant. And the racemic product depends on the situation, just because racemic just means that you have a 50-50 mixture of the enantiomers, which in this case, these aren't going to be enantiomers because they'll be different molecules when we finish. These are just different reaction intermediates, and determined based on carbocation stability, one of them may be preferred. In this case, these carbocations are equally stable, so there's no preference. But we'll get into that next. So, but they're not resonant, but it's a similar idea. So it's difficult to, I don't want to say that that's like completely wrong because you're getting it, but it's resonance is different, right? Because if you just to the resonance structure of this guy, you would be putting the double bond onto one of these carbons, which would then make a negative charge carbon and a positive charge carbon. So that would be resonance, but this is just an intermediate. So they're similar as you can see now, but it's a little different. So hopefully that wasn't too confusing. Any other questions? So this reaction isn't done, which what I was alluding to there in answering that question is now there's a second step here, because now you have a new nucleophile, which is this B minus, and new electrophiles, 2 of them. In this case, they're the same because it's all generic, but it may be different like I was alluding to. So let's say that this B minus binds here, and then we have another B minus that binds here. And you may wonder, where does this other B minus come from? Well, remember, we're dealing with molecules, right? And Avogadro's number is 6 times 10 to the 23. There's decimals, but it's relevant at this point. This is a million is 10 to the 9, or billion rather is 10 to the 9. So this is a billion squared, and then you still have 10 to the 5 more, like increasing power. So what that means is there is a lot of molecules. Even if you have like, you know, millimolar concentration, you still have trillions and trillions of molecules. So this type of thing is happening constantly with millions and millions of molecules, and billions of trillions can't even really understand. None of us can really understand numbers that are that large, but there's just a whole bunch of them, really. So that means that you can certainly draw 2 in your reaction mechanism, is the long-winded point there. So regardless then, B is creating a bond here and here. So we create these 2 products, which in this case, it depends on what R and R prime are for if they're different, but just for sake of a generic example, I'll show them like this. And now to answer the question, both of these would be racemic. So these would create racemic mixtures as a final product. Both of them. If there was no difference in the carbocation stability, which there isn't in my generic example here. So you would have the enantiomeric pair of this one and the enantiomeric pair of this one. I'm not showing any chirality in this case, just because it's a generic example and I want to illustrate the mechanism more than the stereochemistry. Did you say either structure is acceptable? I noticed A and B switch places. So in this case, it would be acceptable. I just want to show this as a generic example. The next one we'll do is specific, and there will be a difference depending on the identity of R and R prime. One of these might be the major product. In this case, since it's generic, they would both be acceptable. And you may see a generic example on the exam. Professors do like to put that on as like a multiple choice question, and a lot of people miss it because it's not a specific example. So they want to, it's meant to be easy, but people miss it a lot because they overcomplicate it. Like here, we're just saying that this is the type of reaction that these undergo. Depending on the specific identities of these things, it may prefer one or the other. But in this case, they're both correct. Okay, so with that, let's do a specific example to show you what I'm talking about now. So the first thing we need to talk about before we do that really quickly is carbocation stability. So this is, there's a rule that higher substituted carbocations are more stable. So a tertiary carbocation is more stable than secondary, it's more stable than primary. So as a quick review, hopefully this is common now, or you're familiar with this, I mean. So this is primary, because to determine it, you just count the number of carbons that are bound to the carbocation, which is the carbon with the positive charge. So that is this one, or this one, or this one, depending on which molecule you're looking at. So this one's bound to just one carbon, and then there's another carbon there, but we don't care. We're only interested in what's bound to the carbon with the positive charge itself. So this is primary. This one has 2 carbons bound to it, so that's secondary. This one has 3, so that's tertiary. So this one is the most stable in order. So in making our double bond, when we break our double bond to make a new bond to like A, like in our generic example, if you created a secondary carbocation and a primary carbocation as the 2 options, then the secondary would be preferred and you wouldn't make very much of the primary. So that's why I was trying to be careful with my words of saying it's a generic example, so it doesn't necessarily apply to this yet in the way that I was just showing, but now we'll do a specific example where this rule will apply and it will dictate what is the correct answer. What's the most stable product? Can you show which carbons you're counting from for each? Yeah, so you're counting on the carbon with the positive charge on each of them. So for this one, it's this carbon, and then this CH3, this counts as 1. This CH3 is the second one. This CH3 is the third one. That's why this one's tertiary. This one, CH3, CH3, so 1, 2, so secondary. This one is CH2, so you count just that one because now this CH3 down here is not bound to this carbon anymore. It's bound to this one. We don't count that, so that's why that one's primary. Yep, no problem. Okay, other questions? Okay, so enough of the general stuff. Here's a specific example that you're likely to see on the exam. So I'll just say predict the product. So the best way to approach questions like organic chemistry questions like this, complete the reaction or whatever, it's to understand the mechanism by which they undergo the reaction, and then you can predict the product without necessarily memorizing, a whole table of reagents. That's a decent way to start, but the class just gets more difficult and you get more and more reagents. You can't possibly memorize them all. So if you understand the types of mechanisms that there are, you can apply that logic to any reagent and then not be caught off guard when you haven't memorized that reagent. So it's best to learn it in this way. It's a lot harder at this point to learn it like this, but it will pay dividends later. So anyway, that's my spiel for learning mechanisms. So that's how I'll always show these types of questions. Once you understand the mechanisms, you can kind of shorthand it and get to the answer more quickly while still understanding the mechanism. So anyway, I just encourage you to do that because I think it's definitely the best way to approach these types of problems. So enough of that. Let's look at our reagents here. So we have a hydrogen and a chlorine. So this definitely is polar and it has a dipole moment, right? And the dipole moment is going towards the chlorine. So this is partial negative and this is partial positive, right? This is also an acid, a strong acid specifically. So, which means that it's a Lewis acid and it's a Bronsted-Lowry acid and Arrhenius acid even for that too. But those are just various definitions basically of the same thing. They're just talking about different aspects of it. So the point is, this is our Lewis acid. This is going to function as our electrophile, this hydrogen here. So this then must be our nucleophile. Again, it's electron rich with the double bond. So that makes sense from our previous examples. So now redraw this once more. So we have our partial positive on the hydrogen. So this double bond will create a bond to the hydrogen. And again, it can bind at either position. And we'll dump the lone pair or the 2 bonds on that single bond to form a lone pair on the chlorine, making it negatively charged. So the hydrogen can go at either carbon. So let's say it goes to this one here first. So that would put the positive charge here, or it can go to the other position. So that would put the hydrogen here. Okay, so which one of these is the more stable carbocation based on our rules we just talked about? I'll let you answer. This is A and B. Which one's more stable? Yeah, exactly. A is more stable because it has more substituents. Right, it's a tertiary carbocation. Right, 1, 2, 3 carbons. So B, this doesn't form in significant quantities. So I'll just put an X through it for now. So this is going to form, and then we also created our chlorine, our Cl minus. So the Cl minus now, this is now our nucleophile, this is our electrophile. So this will go here and create this new bond, and then we would create this as a final product. And again, you may be confused as how I drew it like this. At this point in the class, you can draw it basically however you want, as long as you get the connectivity correct. Right? This is the same thing. It's just when I look at this, you can see that there are two methyl groups and you're creating this new bond. So to make it as clear as possible, you can make these crosses to look like a T and put your chlorine there just to make it a little prettier, but it doesn't really matter. But this is going to be a racemic mixture, right? If it was chiral. This is not chiral because this has CH3s. So this is the only product because there is no difference in, like, if this was a dash or a wedge, it wouldn't make a difference. They would be the same thing. There's no change in chirality. So this is the only answer. So the racemic mixture isn't applicable here. But the only reason I write it and tell you about it is because if this was a chiral position, you would make two products that are enantiomers, and that's the racemic mixture. In this case, it's achiral, so you would just say there's one product, and it's this. But it's still good to remember that if it was chiral, a racemic mixture is possible. And by the way, these are the same thing. So I was just drawing it to show you staying more consistent with the way that it's drawn up there instead of changing it. But these are the same molecule, and both are correct answers. So in this case, this type of molecule or this type of reaction, it's going to make 99.9% of this product, and then whatever's left, a ridiculously small amount, 0.1%, is going to make the other product where the chlorine binds here. And again, the reason that this happens in such small quantities is because this intermediate is more stabilized because it's the tertiary carbocation. So this is by far the major product that is going to form. So questions on that? I'll explain this quickly with a reaction diagram because people get a little bit confused. They're like, I thought more unstable meant it's going to react more, which you're correct. That is the right answer, that if this was formed, this would react more with the whatever you had, whatever nucleophile was available. But since you're talking about reaction intermediate, so you're talking about the difference, but the distance between the, like, where your reactants start and then where your top of the activation energy is. So where the top of the molecule is formed. So I'll draw out the energy diagram to explain what I'm talking about. Is the hydrogen still attached to the bottom right of the molecule? Yes, it is. I didn't show it. I only show it here because it's a part of the mechanism. You're adding that hydrogen here in the mechanism. So I showed it just to explain where that bond went. But remember, there's another hydrogen here as well that's understood at the beginning. So there's really two hydrogens here. I just remove it at the final product because now we're finished with the mechanism. So it would be kind of redundant to include it, but it's still not wrong. You could put it and it would be fine. It'd be correct. So let me draw a reaction energy diagram just to show you what I'm talking about quickly. So if we have an energy diagram and this was our reactants, so if we're going to make the secondary carbocation in this case, this would be our transition state or reaction intermediate here is secondary. Then if you made the tertiary, that is more stable. The tertiary one is here. So the difference between the input of energy that you need for this reaction intermediate is significantly less than this one. So because of that, this forms like a lot more, and that's why we say 99.9% or whatever number it is. It depends on the specific example, what that number is, but it's going to, that's the reason why you get so much of this product, whatever we call this A. Okay, so hopefully that makes sense. All of the reactions that you'll do in this course are going to go through the most stable intermediate. So in this case, it's the carbocation intermediate, but in other examples, it may be not the carbocation, it may be something else. So questions. We will do a different one that is a little bit more complicated. Okay, so now let's do this one. Ooh, that doesn't work actually. Let's just keep it like this for now. Okay, so BR2, or this works for any X2. Hopefully you've seen this type of reaction at this point. It's going to make this. But this is a great example of explaining how there can, depending on the type of molecules and reagents that you're using, the most stable intermediate and the type of reaction mechanism that it undergoes can be different. And in this case, it's one of those examples. So here we know that this is our nucleophile from our previous examples. Here's our electron-rich region. Here we have a bromine attached to a bromine, so there's no difference in electronegativity, so there's no permanent dipole there, but you always have dispersion forces, right? So dispersion forces are defined by an instantaneous dipole that is a fleeting, it's a transient existence, it's not permanent. So, but at some instant in time, there is a shift in electron density that causes this bromine to be positive and this bromine to be negative. So there's a transient dipole, and that's what causes dispersion forces. So remember that, again, there are Avogadro's number of molecules in a flask. So this happens often, even though, like, it doesn't happen a lot, but a small percentage is still a lot of molecules because there's so many. That's what I'm trying to say. So this happens enough that this reaction occurs. So with that instantaneous dipole, then we know that this bromine with the positive charge is the electrophile, just like we did in the previous example. Now the difference is bromine has lone pairs, right? It has 3 sets of lone pairs, any halogen for that matter. I'm using bromine as a specific example, but any halogen, fluorine, chlorine, iodine. So those lone pairs can function as a nucleophile as well. So let's just show this if the lone pairs don't get involved. So if we do it exactly like we just did the previous example, and we have our bromine add here, that would create the carbocation here. If it adds at the other position, it would create the carbocation here. So clearly this is the more stable position, carbocation, from the same rules that we just talked about. So this would form, this one doesn't form. And then the other bromine that we broke off here could be our Br minus, that would go here and then create this. So there's 2 issues with this. These bromines are cis relative to this bond. They're both up, whereas this final product is trans. And the other issue is we're creating a carbocation when we didn't have to, right? So the other alternative, so I'll pause. Did this make sense? This is very similar to what we just did with HCl, I believe it was. Okay. So it doesn't do this. It undergoes a different reaction intermediate. So I'm going to erase everything and then just draw the intermediates that we just we just showed. Just for reference when we do the other one. So the other option is to get these lone pairs involved, as I alluded to. So again, we have our instantaneous dipole and then the lone pair, several of them, but I only need to show one for the mechanism. So this double bond comes in the same way. And then I shouldn't draw it like that. That would be confusing. This double bond comes in the same way, and then this bromine can come back to the other position and form a three-membered ring in the same instant. So, and then this breaks off. So this intermediate would be this, and then the Br minus that we broke off. So let me break this down for you, because this was extremely confusing for me when I was first learning it. I had no idea what these arrows are representing. So this bond, this pi bond, this double bond is forming one of the single bonds to the bromine. So let's say it's this one. And then this lone pair is coming back to form this bond to the bromine, this one here. And you keep everything else the same. So 1, 2, 3. So this is 1, 2, 3. We have this three-membered ring involved with the 2, 3 position. So why is this a more stable intermediate than these? And it's because the octet rule is satisfied by all atoms in this molecule, and it's not in either one of these structures. So if you look at this carbon has 3 hydrogens there, octet rule is satisfied. This has 1 hydrogen, 3 bonds, satisfied. This has 2 hydrogens and 2 bonds, so it's satisfied. And the bromine has 2 bonds and 2 lone pairs, so it has its octet. If we look at this carbon, it only has 2 bonds and 1 hydrogen, and the positive charge, no octet, so this is less stable inherently. Even though they both have 1 charge, these aren't the most stable molecules or things that can exist, but we're only comparing these two. So this one is better because of the octet rule, so this is going to exist. So once again, when we think about a reaction diagram, this one is even lower than the carbocation. So let's say that this is our C pluses, and then this is our bromine three-membered ring. So again, anytime there's a way to make a more stable intermediate, it will form, and that will drive the formation of the product. So now we have this intermediate, and now you have Br minus that can come in and open up this ring. So I'll erase the arrows because that explained a different point. Okay, so now this can come in here and cleave like this. So you may wonder why I'm showing it bind here instead of here. At this point, it's not critical that you know the difference, but it's good foreshadowing to explain. The methyl groups, or any substituent really, is blocking the ability for this nucleophile, the bromine, to get close to this carbon to form the bond. So if that's the case, whenever that's the case, the nucleophile will go to the least substituted site, the one that has the least amount of stuff in the way for the bromine to get there. So that's this position in this case. So it'll go there and open this up, and then this explains the formation of the product. Now, oops, let's draw it better than that, which is this. And that the opening of this ring is why we know that, or partial evidence of some of the evidence why this three-membered ring forms, because if it didn't, you wouldn't have this relative stereochemistry where this one's up and this one's down, trans effectively. This is really pseudo trans because there's no double bond, so it's not actually trans, but you can see how they're opposite relative to this single bond now in this case. So one other thing to mention, this isn't a chiral center here. There's 2 hydrogens, so this can rotate around, but to illustrate the point, this is useful because this applies directly to other to like cycloalkenes doing this type of reaction. Those will make the trans product. So I'll do that next. So questions about any of this? Hopefully it's making sense. I know this is a lot, and I was trying to trying to get through as much stuff as possible, make it as clear as possible, so you guys will be prepared for your exam. So this would be a Z molecule. So E and Z only applies if you have an alkene. So that's why I said that this was pseudo-trans, because there's no double bond. So it's, yeah, okay. So the most specific way to call this is that it's an anti-addition. This is the anti-product. Anti means that anti is the word for this relative orientation for a product that is adding in this fashion, where you end up with a trans-like molecule. All right. So let's do, we probably have time for one, maybe two more. So now, using this idea, which one of these is a correct product? And I'll let you answer. I'll explain, but I'll let you take a stab at it if you want. So A or B? B. Why? B is the correct answer. Trans stability due to lack of steric hindrance. That is correct. The trans is going to be more stable than the cis product, but that doesn't really explain why this forms. And because you could have a situation, and there are different examples like this, where you can only make the cis product based on the reaction intermediate. So the reason that B is formed is because the reaction intermediate allows for you to make B, which is the more stable product. So you're right around the correct answer, but it's always through the reaction intermediate. It's not necessarily the stability of the product, just because you got to go through the intermediate. So unless you input a lot of energy, you can't get over the activation energy for certain situations to get to the more stable product. So let me explain what I'm talking about with a mechanism. So again, we have our instantaneous dipole. So this goes here. Our lone pairs come back to form the three-membered ring like we just had, and then this bromine cleaves off. So the reaction intermediate is this, and then Br minus. So now the fact that this has to come in below the ring and then this cleaves to be above the ring is why the final product is then trans, because this three-membered ring is essentially planar. So the only way for this to access it is if it's coming from behind it or if it comes from above it. So you could also do this. The bromine comes above the ring. So this is why this would be, this would be a racemic mixture with these two, because these are enantiomers of each other. So these are the two correct answers. It's always in this type of reaction with Br2 or X2, it's going to be the trans, excuse me, the trans product, the anti-product. We can say trans in this case now, because you can have cis and trans molecules for an alkane, a cycloalkane, because the orientation relative to the ring is what's dictating cis and trans in this case, instead of a double bond. Like, it's more what you may be more familiar with, but it applies in both contexts. So, questions on that, or we will move on to another question. So have you talked about rearrangements at all in class? Because I think I can use the last few minutes to talk about that if that's something that you're expected to know. It's in the chapter, but I'm not sure if it was discussed in class or not. And I mean carbocation rearrangements specifically. I just said rearrangements, but that's kind of vague. I guess that's a maybe, maybe no. She did. Okay. Okay. So let's do one with rearrangements, because this is in my opinion, this is the hardest type of question in this category of stuff. So let's use HI in this case. So the only correct answer. Let me count all my carbons. 3, 4, 5. So 1, 2, 4, 5. Okay. So this is the only correct. This is the major product by a lot. But if you look at it, it's like how? It doesn't make any sense, because if we just go through our mechanism that we just did, the iodine should only add at 4 or 5. And you'd be right. You're completely right. But again, it's always the most stable intermediate. So it's possible for a rearrangement to occur when you form the intermediate. So I'll walk you through the mechanism here. So we have HI. Again, we have the dipole. So this is positively charged, negatively charged. This is the double bond will function as our nucleophile. And HI is our electrophile. So if this double bond goes here, we can form the carbocation at this position or this position. It's preferred if it's here. So I'm only going to draw that intermediate, because we've already discussed that. So the hydrogen would add at this carbon and make the positive charge there. So now, if you look at this, we have a secondary carbocation and a tertiary position right adjacent to it. When that happens, the hydrogen that's here can migrate to this position. And this is called a 1,2 hydride shift, where we say hydride. Hydride is when you have a hydrogen with a lone pair or with 2 electrons. So this bond and the hydrogen shift to this position. So that's why it's called the hydride shift. And what that does is make the intermediate now, where this is the hydrogen that we initially added from our acid. This is the hydrogen that has shifted from this position, creating the carbocation here. This is now, excuse me, this is now tertiary, which is more stable than the secondary that we had. So this is going to form a bunch more than the secondary option. And then it will get the final product now, where you have the iodine that you created in an initial step that will attack that carbon there. And then you'll make the product that I told you at the beginning was the only product, but now it can be explained. Oops. There. So hopefully that's clear. This is definitely the hardest type of these questions. Why does the hydrogen shift and not one of the methyl groups? If the methyl group shift in this case, it would create a secondary carbocation. You would just go from secondary to secondary. So there's no driving force for that, but I'll show you what I mean. Because you're right, methyl shifts are an option as well. In this case, it doesn't make a more stable carbocation. So if this methyl group goes here, you would make this, which now has a secondary carbocation again. So, but again, now you're adjacent to a tertiary that has a hydrogen. So the hydrogen would shift now in this case, which would make this, which is the same as what we had. Well, I've erased it now, but that's the same molecule. It's just inverted. It's rotated 180, but it's the exact same. There are cases where the methyl shift is the only option that you have. There's no hydrogen there, for example, then it would do that. So we can do an example like that now with we have 3 minutes left. So now to do that, you just add another carbon here, and it'd be like this. So again, now this product is harder to just visualize, but it's going to be this. This is the right product, I believe. Let's go through the mechanism to confirm. But here we have HI. This goes here, kicks this out. You create this. Again, I'm just showing the most stable carbocation because if the hydrogen added at this position, it would put the carbocation here, which is not more stable. It's primary, right? So now there's no hydrogen at this position because it's quaternary. It has 4 carbons there, no hydrogens. So the only option for you is a methyl shift. So if this methyl were to migrate, like I showed to answer that question, you would now create this, where the carbocation has shifted here because you got rid of one of those bonds. So do I have all these counted correctly? 1, 2, 3, 4, 1, 2, 3, and 4. Yep. So this is what would be the right shift product. And then your iodine minus can go here, creating the product that we had there. So there's still this hydrogen here, this one, from the original mechanism. You can also have really crazy shifts where you free the like ring strain. So like in this example, if you were to create the most stable carbocation would be this one, right? And the other alternative is this one. And this is a lot less stable. However, you'll have a significant, oops. We're back? Okay, we're back. So in this case, you'd have a significant mixture of the final products because you could just create the chlorine at this guy and get this product, which you get a lot of that. But you can also have this ring open like this, and you create, oops, you create a 5-membered ring. So 5-membered rings are much more stable than 4 because it's relieving a lot of that ring strain that you have from 4-membered ring. So this will happen also, and then the chlorine can add here, and you get this product. So this would be, I'm not even sure the percentages, but you would get both of these. There would be a significant mixture, maybe like 60-40 or 70-30, something like that. You wouldn't need to know the percentages, but both of these would form. There wouldn't really be a obvious major product in a case like this. So this last example, I would be shocked if it's on the exam, but stuff like this will definitely be on the exam. This is just to illustrate that these shifts are possible even with rings and other types of groups if the intermediate doesn't have any other way to get stabilized. So it is now 11:11. We're 1 minute over. I'll stick around for a minute or two if you have any specific questions. I'll address them now. But otherwise, good luck on the exam. I'll post this recitation at some point before the exam. And yeah, good luck. Email me your questions. I'll try to get to them before your exam next Thursday. Yeah, thank you. Have a good day too. You too.